In this video, we're going to discuss some of the kind of random extra odd carbon naming elements. So, if we have a ring of carbon like this is actually fairly common. 6 carbon rings are very common ring systems. We'll see them many, many times. But here's a bunch of CH2s going around and connecting in a ring. Now, when we have a straight chain, 2, 3, 4, 5, 6, well, if we were to mark the hydrogens, we would see 3 on the ends, 2 on the insides. But on our ring system, they all only have 2. On a straight chain, we actually have extra hydrogens compared to the ring system. So there's these 1 extra hydrogens out on the either side. This gives us a formula of C6H12 versus C6H14. So to turn a carbon chain into a ring, we have to remove those end hydrogens and then bond the carbons to each other. So this means they are fairly physically different. They have different numbers of atoms, they change their mass, they change their shape and size. These are different molecules. Well, how do you describe a ring system? It doesn't really have a chain. Normally we look for the longest chain to be our main chain. You don't have a chain in a ring. It just keeps going around. But you do still have a number of carbons. And so we can still say it's a hex. So while the straight chain over here would be a hexane, it's an alkane that's 6 carbons long. Well, this is an alkane. The ring is an alkane. So it is also a hexane. Oh, we're done. Go home. No more. All right. Legitimately, of course, there's more. They can't both be hexane. These are very different. So what we have to tell you about the ring is that it is a ring. We say cyclo. Cyclo is a prefix to the carbon chain length. It tells us it is a ring of carbons. Now you can get rings that have other atoms in them. They won't be cyclos. This is a ring of carbon atoms. If I've got 5 carbons in a ring, well, that is a pent for 5. It's a pentane. They're all single bonds between the carbons. It is a cyclopentane. And so you have cyclohexanes, cyclopentanes, cyclobutanes, cyclopropanes. And you can get bigger. Cyclooctane tends to be the upper size of what we can make in labs, though biological molecules can have 20 or 30 atoms in a ring. So cyclos are an important but occasionally odd component of naming carbon systems. If you have subgroups on them, so let's go back to our hexane, I will put 2 methyls here and an ethyl here. Well, because there's no end of the chain, we get to pick which carbon is carbon 1. We have that choice. Let's duplicate this. So there's 2 ways I could go about numbering this. You always want, well, if we lack a functional group, you want your substituent, your subgroups, to be as small a number as possible. So I could start down here with 1, and I could go counterclockwise 2, 3. If I'd gone clockwise, it would have been 2, 3, 4. I would have run into my next group at 5. And so if you have a choice on direction, make your next thing you run into smaller. But I also could have started up here with the methyls. 1, 2, 3. So I have a problem. I have the very first thing I run into be a 1. But the second thing I run into changes depending on which direction I go. When we had a chain, we would want the first group we run into to be as low as possible. Both of these situations will give us 1 for the first group, but one of them will give us 1 for the second group, where the other will give us a 3 for the second group that we run into. So if all other things are equal for your first group, you default then down to your second group. You say, all right, well, which one will give me my lowest number for my second group? And so that's going to be the one on the right. And so this will be a 1,1-dimethyl, and it's going to be a 3-ethyl, and it's going to be a cyclohexane. And so we need to piece them together. E becomes before M, so 3-ethyl. Put a dash there between the ethyl and the 1. 3-ethyl 1,1-dimethyl cyclohexane. And so this ring system would be named like this. And so rings, we still kind of name them just like a chain, except we get to pick where we put carbon 1. And so one of our groups will always be on carbon 1 because we get to have it be as low a number as we can make it, and we get to put the 1 on that group. Side note, if I have only the 1-methyl and the 1-ethyl, well, no matter what I do, 1, 2, 3, 1, 2, 3, my numbering is identical in that case. So this raises the question, what do you do if your numbers are going to be identical? Alphabet wins. If you have choices and the numbers for your subgroups will all be the same, but one direction hits a lower alphabetical group first, you take that route. And so my ethyl at the 1 is better than my methyl at the 1. So this is a 1-ethyl, 3-methyl cyclohexane. So some of the oddities that come up for ring systems. Well, other things that can happen, sometimes you have subgroups that aren't just straight chains. You can have this. And so I've got my longest chain. Let's extend this a little farther just to make sure it's very clear. So in this case, my longest chain is 1, 2, 3, 4, 5, 6, 7. This is a heptane. And at the 4 position, well, there's 3 carbons coming off of it. I have a subgroup. But this is not a propyl chain. A propyl chain would be 3 carbons long. And so a propyl would look like 1, 2, 3. This would be a propyl. What we actually have over here is 2 carbons and a methyl. Now there is effectively a subgroup on the subgroup. And yes, this can happen. It can be exceedingly complex. Many, many layers. You can have subgroups on subgroups on subgroups on the main chain. We will not dive into those too deeply. Instead, this has a common name that is so common it is actually official despite the modern naming conventions. If you have a 3-carbon chain where you are attached to the middle carbon, so there's 3 carbons of a subgroup, but you are hooked to the middle up to your main chain. This is an isopropyl. And so this has its own unique name. This is a 4-isopropyl. And so isoprop was the old term for being attached to the middle of the 3 carbons, and it has just survived. It was so common and on so many molecules used in so many industries that we could not shift the name to the modern originally preferred version. Which, just to show you, the originally preferred version was to call it a ethyl with a methyl. And so it would have been a 1-methyl on the ethyl at the 4 position heptane. And so official IUPAC, official modern naming, is 4 parentheses 1-methyl ethyl and parentheses heptane. You can see why people didn't really like that. And so isopropyl is a perfectly valid and far more common way to name this. And so we will use isopropyls as subgroups. And so they're just a slightly different carbon subgroup. There's actually a lot of these, a lot of different 4-carbon groups you can be attached on the end. So let's say I have a really long chain and I've got 1, 2, 3, 4. Well, that's a butyl group. But if it goes down and that carbon it attached to fans out, that is a tert butyl group. Tert butyls aren't names we'll use, but they actually do occasionally appear on a few molecules. And there's also other ones you could connect at the second of a carbon in a chain. You could also connect to the first of 3 with a methyl coming off the middle. And so there are a lot of ways to connect to other things. They all had their own old names, which we won't dive into in this course. Isopropyl is really the only one that survives that will be relevant to us. Tert butyl occasionally shows up in more advanced organic chemistry. Well, on top of isopropyls, there are a few other specialty carbon subgroups. And so let's have a large molecule again. If you go down and you have a ring that has 6 carbons and 3 double bonds. So this is a carbon to a carbon. This structure is called benzene when it is on its own. We'll talk more about that in another video, but it is a very common structure. 6 carbons in a ring with 3 double bonds shows up all over in biology. It is a very common molecule. It's extremely flat. It's very stable. And so it's used to make very flat objects inside molecules. I'll take out one of those hydrogens and connect it to our chain. It is now a subgroup of my chain. My chain again is 1, 2, 3, 4, 5, 6, 7. So the chain is a hept. The chain itself is all carbon single bonds, so it is still a heptane. The double bonds in the ring aren't part of the main chain. So the main chain is still a heptane. Now this works because we're naming the ring as a subgroup. We're not trying to name the double bonds and the ring as our main group. And so 1, 2, it's on the 3rd position. At the 3rd position, we call this a phenyl. So if your benzene is a subgroup, it is a phenyl group. Now this means that the ring carbon directly bonds to the main chain carbon. So this carbon right here must directly bond to this carbon right there. If your ring carbon directly connects to your main chain, it is a phenyl. Why the specification? Well, also extremely common is to have a CH2 and then the ring. If that happens, if there's this one extra CH2 in the way, that is a benzyl. And so this would be a 3-benzyl heptane. And so the difference between the phenyl and the benzyl is that one extra CH2. They are both very common, and so they pop up as subgroups in their own right. And so the 3 subgroups, if you're attached in the middle here, this is an isopropyl. If you are attached to the ring, you are a phenyl. If you have a CH2 and then the ring, you are a benzyl. So in terms of odd, uniquely named carbon subgroups, these are the most likely ones that we will see. And so these are ones that is worth remembering. There's one more odd carbon naming component I want to discuss, and that is polymers. Polymers are when you link carbons together. So if you've got, let's write this out. If I have ethene and I have another ethene, what can happen is you can have various species, we'll just say R, they come in. Well, this causes one of the bonds to break. That carbon makes a new bond with the R group. The old carbon attacks the next double bond. This breaks one of those bonds, causing that carbon to attach and the other carbon to reach to another double bond somewhere. And this just keeps happening. And so the next one will break, connect those together, the next carbon will go off, and so on and so on and so on. The net result of this is that you get we had a carbon with 2 hydrogens. We had a carbon with 2 hydrogens. You've linked all these independent molecules together. So we'll talk about polymerization reactions in the reaction section, but this is just a quick kind of representation for what it does. It links them together. It shuffles how those carbons made their second bond to link multiple molecules together. This is a polymerization. This is how we make plastics. And so polyethylene, this is how you make polyethylene. So most of your soda bottles or anything like that are made out of polyethylene. And that's actually how we name it. The original molecule, the C double bond C, was ethylene. This is the old name. The modern name, the one we learned in alkenes, was ethene. Unfortunately, plastics have been around for a century and they're all named for the old names. But poly and then a molecule name is telling you that it is the linked version of the original molecule. You'll notice there's no double bonds in our polyethylene. Like the ene is been destroyed. The name talks about what molecule was used to make it. So really, if you just see poly and then some molecule, it's telling you you've made a plastic. You've made some kind of polymer. Polyethylene, polyvinyl chloride, all sorts of things. Polystyrene. Probably my favorite is polystyrene. Polystyrene is the old name for 1-phenylethene. If we think about naming that, well, it's 2 carbons for a chain, and it's got a phenyl coming off the first carbon. And so this is 1-phenylethene. What happens, though, is several of these near each other link together. And so as these link, and this one links, and something connects to it, what you end up with is a long chain with phenyl groups. Well, those groups are very flat. They stack very closely, which means they actually hold on to each other really tightly. When you first make polystyrene, it is nearly as hard as diamond. No, styrofoam is polystyrene. But you haven't foamed it yet. The original block, they have to use shaped explosives to crack it so they can then jackhammer it with diamond-tipped chisels out of the vats that they made it in, use giant smashers to crush it. What they then do is, when they first mixed it, they'd sprinkled a little water into the mixture. So once it's crushed, they put it into a mold and they throw it into boiling water. The water inside the plastic expands as it turns into gas and pushes all of the molecules out, fluffing them up. And this is how you actually get the foam. If you ever had a large block of styrofoam, there'll be these little circular rings on the styrofoam. That's actually where a hole in the mold existed, and the styrofoam shot out of it so that it didn't break the mold. When they're done, they cut those little bits off, and what you find those little circles on large pieces of styrofoam, that's where the mold had an opening. And so polycarbon systems, if you see poly in front of the name, it just means that you've linked many carbons together.